Have you ever wondered how atoms behave in the vastness of free space? Picture, if you will, a host of atoms floating in the void, each one like a tiny lighthouse sending out beams of light. This is an example of superradiance, a phenomenon in optical cavities where atoms synchronize their photon emissions collectively, creating a dazzling light show on a microscopic scale. But what happens when these atoms are set free, allowed to roam in the vast expanse of free space? Can they still pull off this synchronized dance of light? The answer is a bit complex. In the wild, atoms can only partially synchronize their emissions. It's like trying to get a choir to sing in harmony without a conductor. As we journey into the world of quantum physics, we'll find that atoms have a mind of their own. In the confines of optical cavities, atoms perform a synchronized dance, emitting photons collectively. But what happens when they are in free space? Imagine atoms as dancers. In a confined space such as optical cavities, they move in harmony, emitting light particles or photons in unison. But in the vast ballroom of free space, their dance becomes more complex. Recent research has dived into this fascinating quantum ballet, studying atom behavior when they are let loose in free space. The results? Intriguingly, atoms in free space only partially synchronize their photon emissions. It's as if our dancers, once removed from their confined stage, can't quite keep perfectly in step with each other. They're still dancing, still emitting photons, but not with the full synchronization we see in optical cavities. Why is this? Well, it appears there are challenges in achieving full synchronization in free space. Imagine trying to coordinate a dance routine with someone on the other side of a crowded room without the walls to contain and direct your movements. It's more difficult, right? The same is true for our quantum dancers. The unrestricted environment of free space presents hurdles to complete synchronization. But don't be disheartened. This doesn't mean our atoms are stepping on each other's toes. Rather, they're creating a new, unique dance that we're only just beginning to understand. Theoretical simulations have been invaluable in shedding light on this quantum dance. They've helped us bridge the gap between the abstract idea and the observable phenomenon, painting a clearer picture of the seemingly chaotic movements of atoms in free space. However, as with any dance, it's the live performance that truly captivates. Experiments have shown that when the energy of a laser surpasses a certain threshold, atoms in free space emit and absorb photons continuously, never reaching a stable state. It's a dynamic, ever-changing routine, far removed from the synchronized dance we see in optical cavities. In the vastness of space, atoms seem to have a different rhythm, a dance that we're only beginning to understand. Theoretical simulations help us understand the differences between cavity and free space systems. These abstract models provide a foundation, but it's the real-world experiments that bring the theory to life. Imagine a dance of light and energy. As the laser energy surpasses a certain threshold, atoms in free space begin to emit and absorb photons in a constant, frenzied exchange, never reaching a stable state. The dance continues, untamed and relentless, defying our expectations of synchronization. This is where theory meets practice, where the abstract meets the observable. These experiment theory collaborations are critical in advancing our understanding of quantum phenomena. They allow us to test our theories, challenge our assumptions, and refine our models. It's a dynamic, ongoing conversation between what we think will happen and what actually happens. It's a bridge that connects the ethereal world of theory with the tangible realm of practice. And it's through these collaborations that we can truly begin to unravel the complexities of the quantum world. The mysteries of the quantum world continue to unfold, challenging our understanding and pushing the boundaries of what we know. So, what does this mean for the future of quantum physics? Well, the implications are enormous. This study opens up a whole new avenue for research. By studying atom behavior in free space, we're venturing into uncharted territory, pushing the boundaries of what we thought we knew about quantum physics. It's like we've unlocked a new level in the game of understanding our universe. Imagine the possibilities. We could potentially develop technologies that leverage these quantum behaviors. Perhaps we're looking at the dawn of new communication technologies, or maybe even quantum computing advancements that are faster and more efficient than anything we've seen before. However, to truly unlock these potentials, we need more research. We need to further our understanding of how atoms behave in free space, how they emit and absorb photons continuously without reaching a stable state. It's a challenging task, but it's the challenge that makes the journey worthwhile. The importance of collaboration between theorists and experimentalists cannot be overstated. This partnership is crucial in bridging the gap between abstract ideas and observable phenomena. It's through this collaboration that we'll continue to advance our understanding of quantum phenomena. As we continue to break quantum boundaries, who knows what exciting discoveries await us in the vastness of space?